going to talk today about momentum in interactions. So if you're opening this, take your own notes. Good luck with that. We're looking for main big ideas. And if you want to play with the Newton's Cradle on your own, I've included some links right here if you want to play with your own later. So let's talk about momentum and interaction. So the momentum when two objects are interacting with each other. So do you remember the law of interactions? The law of interaction said that forces were caused when the two objects interacted, and that one interaction is when two objects are doing the same thing to each other at the same time. The important piece here is it's at the same time. So just like I can't touch the desk without the desk touching me, I cannot touch the desk longer than the desk is touching me. We have to touch for the same amount of time. Also, from the law of interactions, we know that both objects are experiencing the same interaction, so they feel the same size force, remember, but in opposite directions, so a push or a pull equal but opposite. So we have the force of A on B and the force of B on A in opposite directions. So what we have now is the knowledge that the impulse is the amount of force being applied for a specific amount of time. But in an interaction, the two objects feel the same force. Oops, let's put me up here. Feel the same force in the same time, so they're feeling the same impulse, but in opposite directions. Does that make sense? Two objects interacting feel the exact same forces and times, just opposite directions. So we have equal and opposite impulses. What does that mean about momentum? Okay, that means that we have the same but opposite change in momentum. So if they're two interacting, they start with a momentum, they are going to feel a force, and they're going to end up with a change in that momentum. And it's going to be the same change for each, but opposite. So that means if one of them loses momentum, the other one is going to gain that momentum. They're doing the same thing. So it looks kind of like this. We have a positive force of A on B for a specific amount of time, and then we have the negative direction force of B on A for a specific amount of time. So one of them is going to gain momentum and the other is going to lose, but it's going to be the same amount. Yeah? So it causes the same total change in momentum. So let's look at some examples and track this with official notation. So if you count the number of masses in motion and the direction they're going in a Newton's cradle, we can actually see this in action. So let's watch. So one ball was taken and released, and you'll notice that one ball is moving back and forth. So if we track before and after, the before is going to be that downswing coming in on the left, which I guess for you is, I can't mirror, I have to mirror this way. Yep, that's the downswing, and then the upswing would be on the other side, is after the interaction of hitting. So before, give me a second, I'll pause it. On the before side, it looks like this. Oh, that's not the pause button. Whee! Hold on. Okay, so the before, we have one and it's on the downswing, and there's four just sitting there. So the notations we're going to use, we're just tracking momentum. It's the number of masses and what they're doing. So I'm going to look at the number of masses that are moving to the right, velocity to the right, and the number of masses that have no velocity that are sitting there. And I'm going to do that before and after. So in this instance, I start with one mass in motion moving to the right and four masses that are still. And then after the interaction, I have four masses that are still and one mass moving to the right. So this is that in words. One mass moving right is this expression. Four masses still is this expression. And that's going to become four still masses and one mass moving to the right. Now, they're different masses moving, but notice the pattern. Let's see if this pattern continues. This time we're going to start with 2 masses moving and 3 masses still. So 2 masses are swinging down and 2 masses are swinging up. 2 and 2. Okay, 2 stay in motion, 3 of them remain still. There's always 3 still. Watch it, 3 remain still. How bizarre. Okay, so 2 are in motion to the right, plus 3 still, and that turns into 3 still and 2 in motion to the right. It's a different 2 in motion, but there's still only 2 in motion. And this is that in words, for those of you who need words instead of the math notation. But we are doing the math notation, so you see this whole momentum piece, right? The mass and the velocity. 2 to the right, 3 not moving. 3 not moving, 2 to the right. Okay, let's try another one. That was 1 and then 2. Let's release 3. Can you predict what's going to happen if 3 are let go? What happens to the middle ball if 3 are let go? So in this case, we have 3 in motion, 2 still, becomes 3 in motion and 2 still. So the middle one remains in motion the whole time, but the 2 ends go from stopping to moving. But the total remains, it's like the same, right? So we have 3 in motion to the right, plus 2 not moving, and then there's 2 not moving and 3 in motion to the right. It's the same thing. Let's do 4. What's going to happen with 4? Four in motion, 1 still. It like just stops, right? How weird is that? It's pretty cool. Like it just stops. It just stops. It's bizarre. I think it looks bizarre, but it's true because this phenomenon we're experiencing, where they have the same interaction, so they have the same impulse, so they're going to experience the same changes in momentum. Okay, so this time we have 4 moving to the right and 1 still, becoming 1 still and 4 moving to the right. So the pattern we're seeing here is what? What pattern is this? Before and after, we have the same number moving and the same number still, right? The number of masses in motion and the direction they're moving stays the same. But different masses might be in motion, but the same number are in motion. Okay, so what we're looking at is the total momentum before. The total expressions here before, this literally is representing the momentum of both the moving and non-moving pieces before, and that's exactly the same as the moving and non-moving pieces after. So the total momentum before the interaction is exactly the same as the total momentum after the interaction. That's conservation of momentum. Momentum is conserved, is saved, it stays the same. So the total momentum didn't change. What's happening is it's transferring. It's transferring between objects, right? But we still have 4 moving, 1 not moving, 1 not moving, 4 moving. It stays the same. It's pretty cool. So let's codify that into some actual notes for ourselves. When 2 objects interact, what's happening to the momentum? Because we have the same forces but in opposite directions, we have the same impulse but opposite directions. So we have the same but opposite change in momentum. So whatever one gains, the other loses. Whatever one loses, the other gains. That's the law of conservation. Okay, so momentum is conserved. This is the law. It's called the law of conservation of momentum. Momentum is going to be conserved. The total amount of momentum before and the total after an interaction does not change. The total doesn't change. Individually, sure. Total, no. Okay, so the momentum is just going to transfer between the 2 interacting objects, but it doesn't disappear. It's all still there. Now this ends up this is primarily because of conservation of energy, which we haven't covered yet. But it is, in fact, also conserving momentum, which is a very powerful tool for us. So clarify this. Momentum is conserved. The total amount before and after an interaction doesn't change. It's just transferring. But that's only true if what? We have to consider both objects, right? So momentum is only conserved if you're considering both of the objects in the interaction. If I just looked at one set of them, of course this momentum is going to change. You have to see that transfer, you have to actually look at both objects. Otherwise, you're not going to see it transfer, right? So basically, the ones that are in motion are going to lose momentum, and the ones that are still are going to gain momentum. So together, only together do you see a total constant. So when you're doing conservation of momentum, you do have to include everything in the system that's interacting. So all interacting objects must be considered together to see this happen, right? Because if you just looked at the moving ones, they're going to lose it. If you just looked at the gaining ones, they're going to gain it. You got to do both. All right, let's see if this plays out anymore. This is really like the slide, right? This is the big slide. We're going to play more with the Newton's cradle because of course we can do more than just let stuff fall into other stuff. We can let two things fall into each other and see what happens. Why not? So now we're going to have 1 and 4 moving. What? They're both going to be moving in opposite directions. What's going to happen? What? Oh my God. Grown adults and physicists, we play with these all the time. They're still mind-blowing. They're so cool. Okay, so 1 and 4 are in motion, and then 1 and 4 are in motion. It's like the motion just goes through. Okay, so in this case, we're going to use the same notation, but now instead of looking at what's still, we're going to be looking at what's moving in the other direction. So we're still doing momentum, the number of masses to the right, and the momentum to the left, the number of masses to the left. So beforehand, there's 1 to the right and 4 to the left, and then after, there's 4 to the left and 1 to the right. But again, it's the same, isn't it? So that's the notation again in words. 1 to the right and 4 to the left becomes 4 to the left and 1 to the right. In other words, it didn't really change because the total momentum of the system was conserved. So of course it didn't change. Let's do another one. Let's do 2 and 3. 2 and 3, what's going to happen? Bam. What? Two to the right, 3 to the left becomes 3 to the left, 2 to the right. They're doing what? The same thing, but that middle ball keeps switching what it's doing. It's awesome. So in this case, we've got 2 masses moving right, hit 3 masses moving left, starting here. The cycle starts there. And then we have 3 masses moving left and 2 masses moving right. Total momentum is conserved. The same number of masses are in motion in the same direction before and after. Now, yes, this is a special case. They don't always look exactly exact. And we're going to get into what it looks like in the real world when you don't have identical masses. We'll get into that later. But right now we're seeing exactly the same thing happen. Let's get even more complicated. Oh my God, yes, I filmed everything you could possibly do with this. So now we're going to have 1, 3 still, and another 1, but bam, sandwiching, smacking into each other. What's going to happen? Well, of course, it's going to look like they're bouncing off each other. Now, There's a reason I do these last. Because if you're looking at it, you're just like, oh, it just bounced off each other. But no, no, no. You know that the one that's moving to the left is still moving to the left, and the one that's moving to the right is still moving to the right. The momentum is still doing this thing. What? It's not going wonka, wonka, wonka. It's going woo, woo, woo. It's really cool. So our annotation now is how many are moving to the right, plus how many are still in the middle, plus how many are moving to the left, repeating how many are to the right, how many to the middle, how many to the left. So we have one mass moving to the right, one to the left, three in the middle. We have one to the left, three in the middle, one to the right. It's the same. What? It's amazeballs. Okay, one right, three still, one left becomes one left, three still, one right. So the momentum is doing this. It's transferring between them. It's not bouncing. It's transferring between like this. It's very cool stuff. Okay, so the total momentum is conserved. There is one more possibility, and that's 2 and 1 and 2. So why not? What is the annotation going to look like? Can you tell me what the annotation is going to look like? 2 and 1 and 2. So again, we have 2 moving to the right, 1 in the middle still, 2 moving to the left, becomes 2 moving to the left, 1 middle still, 2 moving to the right. The momentum is transferring back and forth like this in a beautiful dance. It's not doing this. It's going all the way through. It's just awesome. So anyway, the total momentum of a system is conserved, right? So here again, the summary of the entire point of me talking to you like this. Okay, momentum is conserved within a complete system. The total amount before and after an interaction between objects does not change. The momentum itself is just transferring between those interacting objects, right? And as a reminder of why, the law of interaction says the same but opposite forces in the same time is the same but opposite impulse. So what momentum one is going to lose, the other is going to gain. It's just transferring as long as you consider both of them together. Got it? Momentum is conserved. It transfers. What? It's awesome. So if you've got that, you can go do the little notes check, and then we'll see how much you got, and we'll get into more complicated examples tomorrow. Thank you for listening. Bye.